Hello everyone. Today I would like to present a universal calculator for optimizing and selecting insulation for ventilation ducts, calculating gains, losses and liquid through the ventilation duct. For this purpose, we use the tool available through this button, module of the calculator for gains, losses and leakage in the ventilation duct. Recently, with the last update, we modified it slightly to make everything more readable. This module allows to select or also check various insulation parameters for both round and rectangular ducts. In this window we enter the initial parameters. Describing the air in the ventilation duct, here we have tip according to our diagram, meaning the initial temperature of the air in the duct, FIP meaning the initial relative humidity in the duct, ventilation parameters outside meaning minus 20 degrees and 100%. This can of course be changed to summer conditions. There are absolutely no limitations here. There is complete freedom. The airstream flowing in the ventilation duct will later determine the coefficient for the air in the duct. Here we have parameters describing the wall of the ventilation duct it is made of. Here we have lambda for sheet steel, the thickness of this sheet. Here we have parameters describing the insulating layer, that is lambda 2 is I assume the coefficient 0.004 watts per meter Kelvin. The thickness of this layer, atmospheric pressure, the speed washing the duct from the outside. From this depends the convection coefficient of air outside and ultimately later the heat transfer coefficient of the entire duct. As a result, we will obtain the heat flow lost by the duct or gained. Here we also have the density inside the ventilation duct and the parameters of the dew point temperature of the air inside the duct and outside the duct, based on which the condensation condition will be checked. Here we will have parameters describing the temperature distribution on individual points, that is on the sheet metal wall here, on the insulation wall and on the insulation wall outside the ventilation duct. Okay, so let's assume we now have a 250 duct with a length of 100 meters. Let's initially assume that we don't have insulation. So let's check this very extreme variant and see what we get from it. And here the program informs us that under such conditions we definitely have condensation of water vapor inside the ventilation duct. Here an icon appears illustrating this condensation inside. Therefore insulation will definitely be needed. Additionally, we have a division between the beginning of the duct and the end of the duct, because there is also heat loss along this duct. As a result of the above, at the end of the duct, we obtain parameters of 7.73, and that is why these temperatures are calculated here for these parameters as well as for the initial ones. So we must definitely apply here. The insulation at the end of the duct settled at a temperature of 7.73 degrees Celsius. Let's assume we use some thin insulation, 2 millimeters, to see what happens next. We calculate and condensation still occurs, but the temperature at the end increased to 10.14. It's clear no one uses insulation that thin, it's just for demonstration purposes, so we can check iteratively. At what thickness of insulation will this condensation stop occurring? With 10 millimeters of insulation thickness, we will no longer have condensation inside the ventilation duct for these 100 meters of the section. However, it is not a satisfactory result, because at the end the air will cool down to 14.4 degrees, so it would be necessary to significantly increase the power of the air heater to raise it to 20 degrees. So let's say we use a more typical insulation thickness for ducts on the roof in winter, and here we see that the temperature will settle at 18 degrees, which is not a small value. Let's not kid ourselves. So we can set it to 80 millimeters. With 80 millimeters, it will be 18.6 degrees. And here we get these values. We can do the same for a rectangular duct. Here, let's say 250 by 250. We calculate. Well, the rectangular duct, as you can see, has higher heat losses due to its geometry, more developed surface, and so on. However, condensation in this case does not occur. We can perform the same calculations for the summer period. That is, let's assume in this case we have air conditioning at a temperature of 12 degrees and 90%. Outside in this case it is 30 degrees and 90%. We can also temporarily disable the insulation here to see what happens to the air parameters at the end of the duct. And here we have information that condensation occurs again outside the ventilation duct. An icon is displayed here. We can do the same for our rectangular one. Here the temperature at the end of the duct is even higher, drastically higher, meaning the rectangular duct loses much more energy than the round duct. Here it has 17, not 9 degrees of temperature difference. Okay, let's introduce some insulation, let's say 80 millimeters right away. And here it establishes that in this case the temperature will only increase by 0.6 degrees Celsius. There is no condensation. The icons illustrating this disappear. The condensation, we have here the temperature distributions in the individual layers in the ventilation duct, both at the beginning of the duct and at the end. And basically this tool is used for that purpose. Besides checking condensation, we can also determine how much power is lost, what the temperature will be, or possibly how much we need to increase the power of the heater or cooler to achieve the required air parameters at the end. That's what I wanted to convey today. Thank you for your attention, and hear you in the next episode. Bye.